We talk about 5-qubit code and what's the meaning of the logical code. And basically, we talked about how to detect an error. And 5-qubit code only detects one error and one type of error in one qubit among these 5 physical qubits. So we're going to talk about logical gate on 5-qubit code, and we're going to introduce another type of quantum error correction code, which is 7-qubit code, sometimes called STIN code. So let's take a brief review of the 5-qubit code again. So basically, it consists of 5 qubits, and there are 4 stabilizers. So I'm gonna use the word stabilizer from now on. So this is one of the stabilizer in 5-qubit code. So even though these gates are simply a quantum gate acting on single quantum bit, we're not actually taking these gates on the qubit. We're actually taking a C0 gate, right? So whenever you see a stabilizer like this, then you have to imagine that there is a control qubit of this stabilizer. Oh, no, sorry. So, yeah, it's a control qubit of this stabilizer, because each of these quantum gate is the target. So the Z gate is applied to the target qubit, which is the qubit 1, and so on. And this is called this is associated to the measurement qubit, one measurement qubit. So and there are 3 more, M2, Z2, X3, X4, M2, and M3. Okay, so this only detects an error, but you don't want to use the quantum error correction code just to keep your quantum information. You want to do some quantum algorithm, right? So we need a quantum circuit with this error correction code. So in order to make a quantum circuit, the most basic gate that you need are X gate and Z gate, right? So how do we make X gate on Z gate on a logical qubit? So let me define the logical qubit here. So logical qubit is the unit of quantum information encoded in quantum error correction code. So quantum error correction code usually denoted as QECC. So 5-qubit code encodes one logical qubit. Okay? And one logical qubit, there are 2 types of base state. One is 0 and 1, right? Every 1 qubit. So imagine one physical qubit. It's always a linear combination of 0 ket and 1 ket. Same for the logical qubit. So as I said, so if you just ignore the second part, the logical qubit is just qubit, unit of quantum information. But logical qubit is different from the physical qubit because it's encoded in a quantum error correction code, which consists of several other real physical qubits. So to distinguish the qubit, the general qubit and the logical qubit, I'm going to put the bar, and that's the same notation which the Mermin used in his book. And 0 is something that it's kind of complicated if you want to write it. So I'll write it in an abstract way, and then I'm going to define it, what it really is, after explaining all this. So this is 0 ket of logical qubit, and this is 1 ket of the logical qubit. So in actual state of if I have to express this 0 cat and 1 cat of logical qubit in a real 5 qubit states, then it's going to be really long, and I can't write it out. So just define it this way, and think about this way. So these logical 0 cat, logical 1 cat act as if it's actually 0 cat and 1 cat in a real qubit. That's the idea. So we want to encode we want to make 5 physical qubits have some quantum information which acts like 0 cat and 1 cat in their logical state. Okay, so we're not looking at actual 0 cat and 1 cat. So once we have that, what we need is how do you make X gate and Z gate acting on these logical qubits, 0 cat and 1 cat. So let's say this X bar and Z bar is the X gate. So we call it logical X gate. On logical qubit. And this is logical Z gate, acting on logical qubit. And it's rather easy to write down the expression of this logical X and logical Z in a real quantum gate, because it's simply the multiple of all X gate on every single physical qubit, and Z for the same. So let's suppose that we initialized our quantum state into cat 0 state, and if you want to apply logical X gate on that state, you just simply apply X gate on every 5 physical qubits. So then you get, you can change, so this means that this is logical X gate, which means that it changes the logical 0 cat into logical 1 cat. So let's try to understand this. So just assume this one is there. So assume that we somehow managed to. I mean, it's really easy to make this state, but let's leave the fact that this is obtained here, and let's see how this gate, this actual gate, work as a X gate and Z gate in a logical qubit. So here's some remark. So first of all, this logical gate commutes with mi for every I. So look at the mi here and look at X and Z bar. So for example, X bar is commute with M0. Let's see. So X0, commute, what does it mean, commute? So it means that X bar mi equals to mi X bar, and Z bar mi is equal to mi Z bar. And let's look at an example of the simple case. So x0, x1, x2, x3, x4, that's X bar. And let's take M0, which is at 1, x2, x3, and at 4. And then M0 again, z1, x2, x3, x4, and then take X bar. So here, the index means that it's the gate acting on that physical qubit with index. But, and therefore, if you have a gate acting on a different physical qubit, you can always commute this order, right? It doesn't matter whether you apply the gate, or you can act a gate on 2 physical qubits simultaneously. The order doesn't matter. So what we have to be careful about is if there is gate acting on a same qubit. So for example, here x2 is x2 here, right? Like this one. And there's x1 and also z1 here. Z1. And there's x3, x4 here. So actually what is important is whenever you have a different type of gate acting on the same qubit, So let's say x2 is acting x2. So there are two x on the qubit 2 with just identity. And really what it means is that you don't care about the order. Because it's the same thing. So it has x2 here, right? But this x2 comes from the x bar, and this x2 comes from the m0, and this one is now m0 x2 is coming first. I mean, actually, this is first, but appears first, and then x2 x on the second qubit from x bar comes last. But really, it doesn't matter because they are the same. So what matters is whenever you have these two. Let me give another color here. So look at this one. So x1 and z1, and this z1 and x1. So now, if you take these two, right? So let me give a differentiation. So we have x1 and z1, and then x2, x2, x3, x3, x4, z4, and x0 first, x0, z1, x1, x2, x2, x3, x3, and z4, x4. So you can see that there are two qubits which differ by the order of the gates here. So this is for the qubit 1, and this is for qubit 4. So when you change the order of application of x and z error, you have a different result, and the result are different by -1. Right? So if you change the order, it must be different by minus, but there's another change of order. So there are two minuses. So two minuses are multiplied. So after all, there's no change. The change are canceled each other. So you can always commute these gates, the logical x and z gates, with this measurement gate. Okay? So that's very important fact, because later I will explain more about this. This measurement qubit is detecting an error. It's used for detecting an error. We saw the table, right? And we don't want to change so whenever you take measurement on measurement qubit, then you get a signature. I call it footprint in the last class, but let's call it signature, like 0010. And this tells you, the change of signature tells you there is or there was an error. However, when you apply x bar and z bar, you're not making an error. You're actually doing some computation. So you don't want to change the signature, because changing the signature means that you're kind of detecting an error. This is not an error. This is a valid gate, valid logical gate. So we intentionally make this in order to change our logical quantum state. So if this changes the signature, we cannot tell the difference whether this change of signature came from the error in the physical qubit or because of this our logical gate. So the error correction actually fails. So this commutativity is very important. So it's kind of meaning that this x bar and z bar do not change the signature. Okay. So let me explain this in more detail. So here, let's suppose that this quantum state on 5 qubit is an eigenstate of eigenvalue E for measurement qubit Mi. So what it means is that, so whenever when you take a measurement qubit and take a measurement, you get 0 or 1 as a syndrome measurement. And then 0 means that your quantum state is stabilized as +1 eigenstate. 1 means that the quantum state is stabilized at -1 eigenstate. And let's say this E is your measurement outcome of your measurement qubit. And for Mi. Then let's see what's happening here. So let's say I'm applying x bar, the logical x on here, and let's see. Before I do that, let's suppose that I applied mi here. So mi here means that actual gates, the collection of gates x and z here, and then let's suppose that I applied x bar. So what is it? So it means that we have e. Let me do one more step here. So because we assume that this psi is eigenstate of eigenvalue e, the result is e times the constant state, and this e is a constant, so it can go outside, right? But then, because we observed the first fact that this x bar is commute with mi, so we can switch the order here. So it means that mi x bar equals to this, right? So what does it say? So this says this is equals to the last one, e x bar psi 5. 5. So let me put the parentheses here. Do you see what is going on? So here, x bar psi 5, or just some logical state here, and the same thing is here. So I can replace it with whatever I want. So let's say this, call it psi. Okay. And on the left-hand side, we say mi is applied to this, and on the right-hand side is e times that, the same thing. So this means that this m psi bar is an eigenstate of eigenvalue e of mi, right? So what's the difference between the original psi? So let's say original psi was here, and then when I applied x bar, it becomes our new psi, the logical state. But they are different. So original state is so you have original state, and after you apply x bar, which means that you apply x gates on every 5 physical qubit, you get a different state. They're different, but they're also same eigenstate of the same eigenvalue. Okay, so I'm not saying same eigenstate. So it's both are eigenstate of the same eigenvalue of the same measurement qubit. So that's the very important part. So there are many rooms to make changes in your eigenstate space, eigenspace. So you see, this is linear algebra. Now, whenever you have a matrix, you have an eigenvalue and you have an eigenvector, and eigenvector which has the same eigenvalue consists of eigenspace, right? So in eigenspace, it could be one-dimensional or two-dimensional and several many-dimensional. And in eigenspace, you can change your vector. You can still change, linear transform your vectors, but still they are in the same eigenspace with the same eigenvalue. That's what's going on. We have psi, original psi, and the new psi bar in the same eigenspace with the same eigenvalue. Okay? But they're different by applying this x bar. So it's same for z bar. So if you see z bar applied to mi, let's say psi 5. Oh, so okay. So let me give a different notation. So psi phi 5, assuming that this is eigenstate of eigenvalue e of mi. Then what? So we can interchange this application. So and then this phi 5. And then if you look at this one, this is e times phi 5. So if you look at this equation here, so z bar applied to the phi5 is also eigenstate of the same eigenvalue of mi here. Okay? So x bar and z bar, application of x bar and z bar does not change your quantum state into different eigenspace. There are only changes within the same eigenspace. So that's why, so whenever you have the quantum state in the same eigenspace, they have all the same signature because they are having the same eigenvalues. Right? You can do this for every m0 to m3. So they have the same signature whenever they are in the same eigenspace. So that's what I'm saying here. The x bar and z bar do not change the signature. Same meaning as not changing the eigenspace. And also, let's look at then also the third fact is that if you take the x bar and z bar in this order and change the order, you will get a negative difference. So this means that x bar, z bar are acting like x and z. Okay. So in fact, there are a few properties of x and z gate here. So when the error correction code gets complicated, all you want is not really the x and z gate on a physical qubit. You want some kind of a collection of gate that acts like x gate and z gate. So the omni condition for those kind of collection of gate to act like x gate or z gate on a logical qubit is this. Whenever you have an anti-commutativity between two gates, you can consider them as, of course there's some more, but you can consider them as an x gate and z gate. So it's obvious, right? So this part, you have a 5 qubits. So now there's the meaning of 5. So it has to be odd. If you take take a x gate and z gate, it's simply x times z for each qubit. But if you switch the order, then it's z times x. So each qubit is added with the -1 sign, but then there's 5 minus ones. Therefore, overall, it's minus. So it doesn't work. So this kind of thing doesn't work with an even number of physical qubits. So very clever, right? So we kind of made a logical qubit with a quantum error correction method possibility, and also we have x bar and z bar applied here. Let's talk about 0 bar. So what is 0 bar and 1 bar? How do you make that? So or 1 bar. So it's pretty simple. So we have so I'm gonna okay. So what happens here is, so we have 2 types of register. One is the syndrome measurement qubit. So measurement qubit here, measurement M0 and M1, M2, M4, I3, sorry. And you first take the initialization of your data qubit and the measurement qubit here. So measurement qubit. And here is your data qubit. So when I say this as a CNOT gate, don't assume that this control gate is attached to the single measurement qubit. They are attached to all the different individual measurement qubit, because there are 4 measurement qubits here, but I just abbreviated as this picture. So in order to make 0 bar, ideally what we want to do is run this circuit once and then take a measurement, have a measurement outcome as 0. 0, 0, 0, 0. The 4 measurement outcome turns into 0, 0, 0, 0. Then you made 1, 0 cat, logical 0 cat. So after run this circuit and have the signature. So now what I mean by signature is the tuple of measurement outcome and have the measurement outcome as 0, 0, 0, 0, then you get 0 bar. You initialized it as 0 bar. Okay. And then how do you make 1 bar? Well, you can make a 1 bar the same way. So assume that you have same thing, and then not starting from 0 cat. So this 0 cat means that every 5 physical qubit is initialized at cat 0. But instead of that, let's say you want to initialize at 1, 1, 1, 1, 1. Okay? So and then you run the circuit. So this circuit here. So basically it's a QACC here. And then you take the measurement, 1, 1, 1, 1. Then you get this 1 bar here. But so this is the ideal case, but that's not really happens. So what happens is you really just take the measurement, and the measurement outcome, whatever that is, you consider as 0 bar. So this is the ideal case. So this can be anything. So if you get 0, 0, 0, 0, you got kind of lucky that your quantum state on the data qubit is initialized at +1 eigenstate for every measurement qubit. 0, 1, 0, M0, M1, M2, M3. They're just a lucky case, 1 over 16 chances, right? But you can get anything. I mean, there's possible of 16 cases, 2 to the 4, and whatever you get, you just consider it as 0 bar. And same for here. You just initialize it to 1, 1, 1, 1, 1, and then run the circuit, and then take a measurement, whatever that is. You consider that as 1, 1, 1, 1, 1, 1, 1, into 1 bar here. Okay, that's the case. And I'm gonna write more technical way of doing this. So here I'm gonna define a projection measurement, projection operator. I think what's the name. Where's the name? Projection operator. Okay, so projection operator. So let's say we have a gate which is satisfied a square equals to 1. So in linear algebra, if you have this, it calls projection matrix or projection transformation. But in a quantum circuit, when you have this, we define PA to be 1 over 2, 1 plus A. So this is projection operator. So what does it do? So let's suppose that we have a quantum state psi, and let's apply the projection operator. So PA is the projection operator, and A has to be satisfied with this equation. And this is 1 over 2 psi plus A times psi, right? So let's say psi, so here is the catch. Because A squared is 1, there are only 2 types of eigenstate. One is it has eigenvalue of 1, and the other is it has eigenvalue of -1. There are only 2 eigenvalues of this matrix. So that's why it's actually called the projection matrix. Anyway, so let's suppose that this psi originally was eigenstate of eigenvalue 1. Then what happens? Then A psi is just psi, so it's twice of psi, so it becomes psi, right? So let me write the case here. If psi is plus 1 eigenstate, then it's a psi. And what happens here? If psi was minus 1 eigenstate, then what? 0. It kills. Okay. And so do you see what's the meaning of that? So this projection measurement kills the component which is on the other part of the eigenspace. So the eigenspace consists entire quantum state, and then it kills all the part that is in the other side of the eigenspace. It only preserved the eigenstate where it was. So it only preserved the eigenstate of eigenvalue 1. But there's another projection operator. So let's say we have PA equals to 1 over 2 I minus A. Let's see what happens when I apply PA to psi. So then, let me write it here. 1 over 2 psi minus A psi. And if A psi is equals to psi, if it's plus 1 eigenstate, then it's killed, right? And if it's opposite, then it's preserved. The same thing comes out, psi, right? So depending on, so this is not really a gate. This is just an operator, the ideal transformation as a matrix or linear transformation. It's just you can imagine in your calculation. You cannot implement this, but just saying that whenever you have a measurement outcome of 1 after taking a measurement gate of M0, then you can consider that you applied the projection operator of this type, and if you got so let me clarify this what I just said. I think I made a mistake. So let me write it down here. So we mark if you read C, it could be 0 or 1 on measurement MI, then it is same as applying PMI plus C, which is given by 1 over 2, 1 plus, so I plus minus 1C MI. That's what I'm trying to say. Okay, so let's suppose that you read 0, 0, 0, 0 at the end of the measurement. That means you applied 4 measurement gate on the physical qubit. So it's same as, so whatever your quantum state was for the first time, let's say 5, it was, let's say right here, psi 5. So first you applied M0, right? But the measurement outcome for the measurement qubit M0 was 0. So it's same as applying this. Okay. And then you apply M1 and take a measurement and you got 0. So then it's same as applying this. And so on, right? Until you get the last one. Okay. So that's the quantum state you get after taking the measurement of your quantum circuit, one cycle of this quantum circuit. Okay. So, I mean, if you want, you can write it down the detail, but it's gonna be really complicated. So so if you want to write down the 0 bar and 1 bar as a linear combination of quantum state, this is how it looked like. So 0 bar, how many 2s? So there are 4, so 16, M3, M1, sorry, M2, M1, and M0 of 0, 0, 0, 0, 0. So this is the quantum state, the actual quantum state on a 5 physical qubit. And 1 is the same thing. Here. Okay. Any questions so far? So now we're kind of ready to move on to the 7 qubit code. So I want to have any questions. Yeah, question? Yes. So here I'm assuming that the measurement outcome, the read off of all the measurement qubits is 0, 0, 0, 0. So okay, so here's the case. So when the signature is x0, x1, x2, x3, then when you run the circuit, it is as if you take a operator minus 1 x3 m3 plus minus 1 x2 m2 and minus 1 x0 m0 on your quantum state. So then I need to write the words here. So then the quantum state after this measurement, after the syndrome measurement, is this. So it's kind of, we're looking at backward direction. So you run the circuit, you read the signature, and then you imagine that if I write down my quantum state as an equation, then this has to be what it is. So I'm not saying that, okay, so I'm gonna expect this to be, and then take the measurement. No, we cannot expect that, right? So you just run the algorithm, run the computation after you take the measurement. Any other questions? Yes.
여기서 우리가 다뤘던 거는 메저먼트를 네 번을 해가지고 큐빗이 네 개인 경우를
Yes. Yes.
그러면 메저먼트를 다르게 하는 경우도
So you want to change the measurement? You want to change the order, or you want to change the gate? Number. You want to increase the number of the measurement gate. So 5 qubit code is just having 4 measurement gates, no more. Always. I mean, that's the definition. You can create your new quantum error correction code. I'm not saying this is the only one. Like, there are infinitely many. I mean, you can even increase it to 10 easily, right? You can just run it twice every time. Yeah, so that's why I think as in the beginning of our semester, I mentioned that there are 2 big pillars of quantum computing science. So quantum computer and quantum computing is different area of research. Quantum computing involves physical materials and all the others. Computing part has 2 pillars. One is algorithm, the other is error correction code. So algorithm, of course, it's doable, but imagine what's the most important algorithm that we have been found so far. It's the Shor's algorithm, and Shor's algorithm is almost 20 years ago, more than 30 years ago now, right? So within this 30-year span, they didn't find more powerful algorithm than Shor's algorithm. So kind of means that finding good algorithm is very hard business. And also some people actually having a doubt that this quantum computer will not change the world, because we can't change other than, I mean, the Shor's algorithm is the best we can do, and there's no other chances that the quantum computer or quantum computing can improve our computing business. But anyway, the other pillar, the quantum error correction code, it's quite doable. I mean, I think in my perspective, the recent research business on quantum computing is about how to use quantum computer in AI, which is the algorithm part, and the other parts is quantum error correction code, or in some way connected to quantum error correction code. So another reason why I think quantum error correction code is doable business is that there is no quantum computer yet. There's no effective quantum computer. So everything they do on quantum error correction is kind of ideal theoretical research. So you can do anything. I mean, any research is kind of received as a valuable one, because we don't know what's going to be the best, right? So once some company or someone make a quantum computer which is quite good, which means that it has a large qubit and with kind of and also scale up, then people might want to fit their quantum error correction code into that quantum computer. Then it kind of narrows down to the area of research on the quantum error correction. So now I think this is the right time if you want to pursue some research on the error correction code. So any other questions? So we can go through the 7-qubit code quickly. So since we talked about projection operator and everything, now so this is called the STEAM code, and there are famous type of code that's called CSS code, and the STEAM is one of S, and as name indicates, it uses 7 physical qubits to encode 1 logical qubit, and there are 6 measurement qubit. So these 3 is about X, and these 3 is about Z. So you can see they are kind of twins each other, right? So index are the same. Only difference is that whether the gate is X or Z. And you can change the index, but the idea is the following. So here M0, M1, so let me write down here. M0, M1, M2. So I'm gonna put a mark where it has X gate or not. So on 0, 1, 2, 3, 4, 5, or 6, 7. 6, 7 here. Okay, so is there X gate? Is there X gate at the qubit 0 on M0? Yes, there is, right? Is there X gate on qubit 0 in M1 gate? No. Is there X gate on qubit 0 on M2 gate? No, right? So I'm gonna do this for the 7 column. So on the first qubit, where is X1? Omni M1, right? Where is X on the qubit 2? They're omni 1 in M2. On 3, where? Here and here. X4 is here, here. X5, here and here. X6, here, here, here. Sorry, so this is 7, right? We used all the 7 qubits here. Okay. So you see none of them are same thing. So I don't see the same signature everywhere. They're all different. Now, how do we use this? So the quantum circuit is like this. You have 6 measurement qubit and 7 data qubits, and let me abbreviate like this. Doesn't matter what order you take. So here it's M0 to M2 and N1, 0 to N2. So there are 6 measurement gates here because of the 6 measurements here. And the control is on each of these measurement gate, measurement qubit. And this is the circuit. So now let's just look at this part because we are looking at MI. What does this part do? This part, the MI, only consists of X. So it only detects a Z error. So measurement X gate can detect whether there was Z error or not. It cannot detect X error. And then the signature are all different. So what if we had X error on the qubit 0? Z error on the qubit 0. What if we had Z error on the qubit 0? So let's think about the measurement outcome. So the signature, let's say the signature is X0, X1, and X2. And let's say we had, let's put a bar here, a tilde here, to indicate that this is an error, not the actual gate. So let's say we had Z error. So these are measurement outcome of MI. So what happens? What is X0? So suppose that we had, no, you don't have to suppose it, yeah, right? So just what is X0 when you have Z0? So M0 has X1, X0 here, right? So it will change it to 1, right? How about M1, M2? Can you detect Z0? No, because it's nothing to do with this qubit 0. There's no qubit 0 on M1, M2. There's no X0, right? There's nothing attached to the qubit 0 for M1, M2 measurement. So you don't detect anything here. So if you have Z0 error, the Z error on the qubit 0, your signature will change it to 100. We're supposing that our first initial signature was 000. Okay. How about Z1 tilde? We have a Z error on the qubit 1. What about M0? What's X0 here? It's going to be 0, right? There's no X1, so no change. And how about M1? There's X1 measurement, so it can detect an error. And how about M2? There's no X1, so we don't detect an error, right? So you can imagine what happens at the end, right? So since every signature on these columns are different, you can detect an individual error up to qubit 7, right? Qubit 6. All the 7 qubits. So now you can do the same thing for X error. So in that X error, you go for the measurement outcome of NI measurement, not M. So here we have error. And let's say Y0, Y1, Y2. So that is the measurement out of Ni. Okay. So let's say we have X0 error here. So X error occurred at the qubit 0. Well, it's the same thing exactly. So 100, X1 error, then you get 0, 1, 0, and so on. Yes? Oh, that's right. Oh, yes, there's a typo, sorry. So 1 here. Thank you. Okay, so Why do you see why it's better than 5-qubit code? So it uses 2 more qubits. It has to be better. What's better? So in 5-qubit code, it can detect one type of error on a single qubit. But here, it can detect X and Z error independently, right? And still, it can detect only one error of one type. So, but let's see. So here in X5, Z5, what is the signature? It's 110, okay? So if you got 110 as your result, then you can imagine that this is coming from one Z error on a physical qubit 5, right? But it could be there were 2 Z errors on qubit 0 and qubit 1, so that it gives 110. So there are possibility of having 2 errors, but in that case, this error correction code cannot tell you which one it is. So we are using this quantum error correction 7-qubit code in an assumption that there is a very rare chance of having more than one error. Okay, one type of error. One type of error in a one qubit, more than 1 qubit. So same for here. Okay, so 7-qubit code can detect an X and Z error on a single qubit. This qubit means physical qubit, not logical qubit, independently. That's the important. And everything else is the same. So because of it can detect X and Z error independently, the better thing is that the thing is that we can apply logical Hadamard. There is logical Hadamard gate applied. So first of all, X gate, logical X gate is X0, X6. And second, Z is Z0, Z6. Okay? And third one, it's very confusing. I mean, it has to be this way, but I'm not saying this is generalized. So logical Hadamard is also possible. So this was possible for 5-qubit and 7-qubit code, right? 5-qubit code, you have X error and Z error with the same kind of way, that X errors on X gates on every qubit, but this is only possible on 7-qubit. This is not possible for 5-qubit, so which means that even if you apply Hadamard gates on 5 physical qubit and 5-qubit code, it will not act like Hadamard gate. So let's see how it works. First of all, well, this is kind of obvious. I mean, it's maybe not obvious, but let me use the same notation here. So 0 is, let's see, here, 0. So I kind of have to work on with this coefficient. The book says this is 3/2. I have to make sure why it's not 1/2 to the third. But anyway, so let's leave out the coefficient part later, because that's not really important. The coefficient is always rescaled so that the final result is normalized. So that's 0, 7 here. So that's the logical 0. So you run this measurement qubit mi, all of this mi, on 0, 0, 0, 0, 0 physical qubit, then you get the logical 0. And 1 is kind of different. So instead of using m, we use n. 2 on 1, 1, 1, 1, 1. Okay. So that's your logical cube 0 and 1 in a 7-qubit code. And then let's see why why is that X bar and Z bar is actually the logical X and logical Z. So first of all, what happens when you apply X bar on the logical Z, logical 0? It has to be logical 1, right? Let's see what happens. So we have X0 up to X6, bar here, right? And then let's not take this, consider this coefficient right now. And then have M0, M1, M2, right? And 0, 0, and 7, okay? So first of all, I'm going to somehow move this X0 to X6 all the way up to here. I want to switch the places here. So in order to switch the place, I have to think about the commutativity with M0, right? So X0 to X6, X bar, is it commute with M0? Of course, right? This is all X, right? X is commute with X, right? So I can move this all, yeah, X bar. It's M0, right? So let me check if I made any mistake here. So 7-qubit code. Here's so 1. Oh, sorry. So this is not N. This is M. This is M. Okay. So when I move this, so I can switch the order here. X0, X6, and then M1, M2, 7, right? And then I switch the order of these two by looking at the commutativity, and then M1 is also consists of X, so I can still change it. So what I do is I do all the way down to here. I put X all the way down to here. So and then when I apply X0 to X6 on this 0 cat on every physical qubit, I get 1, 1, 1, 1, right? So what is it? This was, by definition, the logical 1, right? So I changed the logical 0 to logical 1. And let's see what happens when I apply Z bar. So when Z bar is applied to logical 1, what is it? So it's a Z0, Z6 applied to what? 1 plus M0, 1 plus M2, 1, 1, 1, 1. Okay. So I also want to do the same thing. I want to put this Z gates all the way down to here so I can apply that. Now, look at this. These two. So 1 is okay, so identity gate, so I can put it on the right. But how about M0? M0 has 4 X's, right? So there are 4 places that has Z and X. So if you want to change the order to X times Z, you have -1 comes out. But there are 4 minuses, 4 minus 1s, because there are 4 X's. So therefore, overall, there's no change. There's no change of coefficient. So you can simply change to 1, M0, Z0, Z6. And M1, M2, 1, 1, 1, 1, right? So after you do this all the way down to here, you get M0, M1, M2, and then now Z gate applied to 1 cat, get -1 cat. How many Z's are there? 7. So -7 minus 1 gives to minus, right? So now you get put minus here and still 1, 1, 1, 1. So these things were supposed to be logical 1, and you get minus. So Z bar is acting like Z gate on the logical 1. Now let's look at the Hadamard. So when we say Hadamard, what we are expecting it to be this. And this. Right? So if you want to work on, then I think you can, but it's better to say what I want is when I have this quantum state, and then I take the inner product between these two, this one and the zero cat, which is the bracket operation like this. I want 1 over square root of 2. And I want the same thing for 0, Hadamard, and 1. So it's not a special notation. I'm just putting bra, which is the dual of the 0 bar cat, with this H 0 bar. So this is just the inner product between this quantum state and this quantum state. So when I do that, so this means that basically you only get 50 chance to observe this one and this one, right? So the non-zero value occurs only when you take the inner product with this or this. So when you get this inner product, you get 1 over 2, and also for this, and also for this one, here, 0 bar H, 1 bar, and when I take the inner product with 1 here, you get minus 1 over 2. So all I want is this. So let's compute the first part. So we have 0 bar. So let me consult book here. So let's see. All right. So this is the dual of 1 plus m0 all the way up to 1 plus m2, 0. So I just want to make a dual of this 0 cat and dual of this operator. Dual of operator is a Hermitian. So when I take mi dual, it means that I take as a matrix, I'm taking a transpose and conjugate. Take a transpose conjugate. But look at this mi. Look at this mi. They are all X gates. So when I take the dual of this one big gate, and I'm taking dual of everything here, and also I have to switch the order. But switching order doesn't really mean anything because they are all commutative. And when I take a dual of X gate, it is X gate because X gate square is 1. It's just the inverse of itself. So the dual is the same thing. So this is same as 1 plus opposite 1 plus m0 up to 1 plus m2. Okay. So let's try to compute this. The first part here. So we have 0 bar 0 0 0 0 0 0. Okay. So 0 0 dual of 1 plus m0, 1 plus m2. Now h bar is h0 to h6, and then 0 bar here. So it's 1 plus m0, m2, 0, 0. Okay. So all I need is just to see what happens in between. And here's the funny thing. So 1 is okay. So what I want is put h on the other side and then somehow combine this m part together. But look at this m. So you see x, if I take m0, h0, what happens? So first is x0, x4, x5, x6 times h0. So it doesn't matter what other qubit's doing. It's only for the qubit 0. Now we have 2 gates. But then if I want to put h on the left-hand side, I have to switch the order of x0 and h0. But then we have identity, this identity. So in other words, if I take Hadamard in between x, it turns into z. So this has to be the identity that I have to explain at the beginning, but well, now it appears. So if you are curious of why is it true, then you can just work on 2x2 matrix and see that is true. So when I change these two, I get h0, z0, x4, x5, x6. Okay, so x is turning into z. X is now turning into z. So now you can see what happens when I apply h bar here, not h0. H bar is consists of h0 to h6. So I do this for every qubit. So if the qubit x gate is not appeared here, then it doesn't matter because it's nothing to do with this qubit. But when it appears, then there's at least one Hadamard that changes the order and turns x into z. So this will become h bar, z0, z4, z5, and z6. Right? Every x is now turned into z. So what is this? This is h bar n0. Right? So when I move these all the way down to here, or let's say think about this, the opposite order. Order doesn't matter. So when I change the order of this and these, it becomes 1 plus n, right? Okay, so let's finish the computation here. So what we have here is, yeah, so we have 0h0 is equal to, so I have h gate. So okay, so what I really wanted is not putting h on here. I want to put h on here, sorry. So h on here, it's the same thing. So the m's on the right, on this part, is now becomes n, right? So let me write down that here. So we have 0, 1 plus m0, 1 plus m1, 1 plus m2, 1 plus n0, 1 plus n1, 1 plus n2, and then Hadamard from h0 up to h6, 0, 0. Okay. Let's see. Okay, so I think I need to do something more work on here. It's not simple calculation here. Since we have no time, I'm gonna redo this part next time. So this computation, you have to switch this part again. So it's kind of doing the part again. And basically what we need is we need a coefficient, a real coefficient here, so that it becomes 1 over square root of 2. So yeah, sorry for that. Let's do the computation next time.